Very good afternoon, and I welcome you all for the parallel technical session number 16, Hall D. I have the pleasure of inviting the chair for the session, Engineer Srinivas Mantrala from Afghans Infrastructure Limited. And also I welcome co-chair Professor Jayarajan P from NIT Calicut. And in this session, we have a SOAP lecture by Mizanur Rahman from the University of South Australia, and followed by other presentations will be there in this session. 5 presentations will be there in this session now after this SOAP lecture. Now, on behalf of the organizing committee, I welcome Srinivas Mantrala. And Srinivas Mantrala is the Vice President of Afghans, and he is a graduate in civil engineering from NIT Warangal and postgraduate in marine geotechnical engineering from I.I.T Madras, and currently is pursuing PhD from I.I.T Madras, I believe. I extend a hearty welcome to you, sir, on behalf of the organizing committee, and request you to chair this technical session.
Thank you.
I also welcome Professor Jayarajan P from NIT Calicut. Professor Jayaraj, he is professor at NIT Calicut, and his area of research is in soil dynamics, dynamic soil structure interaction, and performance-based earthquake engineering. On behalf of the organizing committee, I extend a hearty welcome to you, sir, and request you to co-chair this session.
Thanks a lot, sir.
Now, it is over to the chair and the co-chair to carry forward this session. Please, sir, over to you.
Good afternoon, everybody, and particularly Professor Mizanur Rahman. And liquefaction is a very important phenomenon to be taken care during earthquakes. And I'm sure most of you must have come across with a recent WhatsApp message showing the liquefaction happening in some parts of Assam, where there was a recent earthquake. You know, it's talking and listening is something different than seeing with our own eyes. The ground was virtually moving, and people are really afraid of standing on the ground getting liquefied. It's practically held because of the grass on the top layer. It is on the ground. But nevertheless, in India, all along the boundary with Himalayas, that area is prone for seismic activity because of the geomorphology. At the same time, we are having our Indo-Ganges plains are there all along this boundary, and this area is prone for, all the structures are prone for liquefaction. Given this background and the study of liquefaction is very apt for this conference, and I thank the organizers to give me the assignment to be chair of the session. I'm extremely grateful to them. And now I take the privilege to introduce Professor Rahman. Professor Rahman did his PhD from University of New South Wales in the year 2010. And for his extraordinary work, his work has been given gold medal, which is a rare thing. And in a short span of 10 years from his PhD, he rose to the position of associate professor and heading 3 academics, and he is guiding today 10 PhD students. More important is, like I come from industry. He is working in the area of transferring the theoretical knowledge into actual engineering applications in the field. I'm sure it has a lot of value, and that can be seen from the very fact that he is having projects worth $2.3 million. He is guiding, which transfer into actual execution on the field. And I'm sure his CV is going to be, or he will be a role model for all the PhD scholars to put in active work and emulate him and rise quickly in the career. Now, I would request Professor Rahman to take over and share his knowledge with all of us. Dr. Rahman, please.
Thank you, Professor Srinivas. It's a big introduction for me. Okay, I'll share my presentation and then I'll start talking about what I'm working about nearly 15 years. So, and I'm hoping that most of the people would have access to my paper. So the presentation would link with that. So the topic of my presentation is equivalent state theory of silty sand, and I'm pretty sure probably you haven't heard about this theory yet because it's just starting. The work I'll be presenting, it's 16 years of work with many renowned colleagues, and I need to acknowledge them, like Professor Robert Lowe from University of New South Wales, Professor Yanis Dafalias from University of California, Davis, Professor Mishko Chibroniski at University of Canterbury, Christchurch, Professor T.G. Sitaram, Institute of Technology, Guwahati, led Professor Tom Shans and Mizanur from Ruhr University, Buckham, and Antonio Carrillo Imperial College. I would also like to acknowledge many of my former and current PhD students, particularly Dr. Abdul Baki, Dr. Koinian, and Dr. Nick Barnett. And for this kind of research, we haven't got industry funding, but it was supported by federal and state governments funding. So these are the content of my presentation. First, I will talk about what is sandwich fines. It's probably new to most of you. It's particularly, we can say loosely, silty soil, but it has a very specific explanation. So I'll talk about that. Then I will talk about the problem with sandwich fines. When Professor Sibanar was talking about soil liquefaction, you may remember like soil liquefaction in Christchurch, New Zealand in 2019 and 2014, I was there and I have first-hand experience on soil liquefaction. And it's particularly a problem for sandwich fines. Then I will introduce some density concept like void ratio, then equivalent density concept E star. From there, I will go to equivalent state and few of its application, particularly critical state and critical state line and critical state soil mechanics framework. Then I will give you an example of soil liquefaction assessment for Ahmedabad sandy soil. I just picked this example so that people from India would be interested in it. Then I will talk about how can we implement this concept in few constitutive models, including cyclic constitutive models. First, over here in this work, we define sand, any particle size bigger than 0.075 millimeter to 2.36 millimeter. But most importantly, smaller than that is fines. And most of the fines in this talk would be non or low plastic fines. So in this figure, we have the right axis, the particle axis is percentage finer, and x-axis is particle size. This is 0.075 millimeter size. This is a clean sand grain size distribution. This is uniformly graded sand, and this is fine grain size distribution. Over here, we systematically increase fine content in the sand. So if we increase fine content, this is 10%, 15%, 20%, and 30%. So if we go 100% fines, it would be silty soil, silt. If we go 0% fine, it would be clean sand. So we could look at the transitional behavior. Now, what is the problem with that? So if we have a soil sand with 10% fine, and if you treat it as a single soil, then we do not have any problem. We'll do the test, we'll understand the soil behavior, and we can implement this understanding in our design. But in reality, what happened, a single soil may be mixed with different percentage of fines. Then the single framework doesn't work. So people from the very beginning try to develop a single framework. And when you try to do that, you have lots of problems. So I present some of the example over here. For example, Question and Shang, they use medium sand and use non-plastic silt increase from 0 to 60%. What they observe with void ratio, with same void ratio, the strength decreases or liquefaction resistance decreases. They didn't compare with the relative density, so we'll not talk about that. But again, if they change the medium sands to fine sand and use the same silt from 0 to 60%, they observe something interesting. The strength increase up to 5%, then decrease. There is some other example, even if you look at the Ottawa sand, 3 of them over here. For example, Carroll fine, the strength increases up to 5%, then decrease. The others, they find is always decreasing. So if we have a consistent trend of decreasing, then we could add a reduction factor with the clean sand, then we could use in design. But in this case, it's not the case. So the comparison basis, whether we're using relative density or void ratio, is not consistent over here. So for this particular type of soil, I need to, or I like to start with the basic concepts. So over here in this figure, I have a schematic diagram of sand particles. These are the sand particles randomly distributed, and in between we have void space, maybe filled with water. So the void ratio of this particular arrangement would be volume of void divided by volume of solid. So for this arrangement, the void ratio is constant at the moment. With the fabric, if we change the orientation of the particle, it might change, but let's do not talk about fabric at this moment. But for this arrangement, this is the void ratio. So for this void ratio, we have particle contact points. When you apply load in this soil, the load would be transferred through the contact point. So what does it mean? This void ratio represents the skeleton structure of the soil, that is its resistance capacity. But in this soil, if I somehow manipulate these and add some fine content in between the voids, these fine content are not contributing to the skeleton structure. They are not taking any force. But what they are doing, they're increasing the solid content in the void ratio calculation, decreasing the volume of void in the calculation. So their void ratio is decreasing. So what we would expect, the void ratio of clean sand would be higher than void ratio of sand with fines, but the same skeleton structure. But they might have the same resistance, because if we applied in the soil some load, then they would be transferred through the same skeleton structure. So these are the inconsistencies we're observing. So one example you can see over here, these data come from Maliki. They use clean bubbles or sand and sand with 10% fine. Here is their triaxial test data. Y-axis is diabatic stress and x-axis is axial strain. So what do we see? Both sand with 10% fine or silt or clean sand has the same behavior, same strength, peak strength, but their void ratio is different. 10% silt is smaller than clean sand. And ideally, if we look at the same soil, then lower void ratio mean higher skeleton structure, more density of contact, higher strength. This is not we see over here. So void ratio is not consistent. Let's see another example over here. This is from Corbis, who first used the equivalent void ratio concept. That's why I picked this figure over here. This is triaxial test data for bendamine tailings and Kamloops sales. So what they have done, they increased the seal content, 4%, 0%, 4%, 7.5%, 13.3, and 22.3%. The compression side and extension size behavior almost same, except in our compression side, a little bit different in higher fine content. So what happened over here, as we increase the fine content, as you see, the void ratio is decreasing, but more or less their behavior remains same. So this void ratio, the global void ratio, is not representing their skeleton structure, not representing their strength. So what they have done, for the first time, they're considering this void over here, these fine particle over here as void. based on that, they're calculating a skeleton void ratio equivalent to clean sand void ratio. When you do that, then we can see the void ratio become consistent, except with too high fine content. Okay, let's move further, see what happened. If we understand that if void ratio, we need to modify it to equivalent granular void ratio, then we come up with some equations. So Thebana-Yagam first introduced this equation to modify these global void ratio to equivalent granular void ratio. For this particular case, he's assuming all the fines over here are not contributing to the solid skeleton structure, not contributing to the strength, so they can consider this fine as a void. This equation you might see in many different forms, but this is a simplistic with some assumptions. So over here, if we assume everything is fine and not contributing, then you can transport them to equivalent granular void ratio this way. But over here, if fine content is higher, then some of the fine may come in between the contact between coarse grain, and they will contribute to the strength. So in this case, we have to consider them. So he modified, or they modified, their team modified this equation this way, where B represent the active fines, that is the red small fine particle over here, the fraction of active fine. These two formulation is internally compatible. For example, if we assume no fines are active, then B equal to 0, then this equation transferred to that equation. That equation is actually this. If there is no fine content in the sand skeleton structure, FC equal to 0, then the void ratio, equivalent granular void ratio, become the void ratio of clean sand. So this is nice and compatible. But the problem is, how do you get the B for active fines? We cannot see grain to grain contact. So how can we get it? So what do we have to do? We have to find some test data and try to find out what would be the equivalence. I will not talk about this today, but I will show you the history of the development. So when first Thebana-Yagam presented this E star equation with B, he assumed about 1/4 of fine would be active. So B equal to 0.25, and it's constant. It doesn't vary with fines content. But later, they published another paper as a reply. They said that B for different sand with fines varies with uniformity coefficient of sand with fines and diameter ratio. In 2004, Ni proposed that actually this B depends on the particle size, Xi. D10 is the 10% finer of clean sand, and small d 50 is 50% finer size for fine size. In 2008, during my PhD, I realized it must be related to particle size and also the fine content. If fine fits in the gap between the coarse particle, then if the fine content is significantly enough, then they must come in between the coarse. So based on that, with some growth theory, we come up with semi-empirical equation like this. In this equation, we had two fitting parameter M and N. And then another later paper we published for 9 different data sets, we could just assume N equal to 1 and M equal to 0.3, and that satisfy wide range of data. Another equation published in 2014 by I.I.Sc with like this. This is also empirical equation with another parameter is roundness ratio. So he has fine content and the diameter ratio. Mohammed and Qadami is actually reanalyze our data, my equation, and suggested it could be simplified this way. Chen and Deng, they propose another equation. It's come from a slightly different theory, so it's a very interesting one. With DEM analysis, discrete element model analysis, there is other theories come in. So I'm not discussing over here because they're much more complicated. Now, whatever the equation for B we use from here, it's not the important thing over here. The important thing, if we get an appropriate E star equivalent granular void ratio, then whether we can further go ahead with some theory development. I have used lots of data from literature, mostly using the equation over here. For example, some list in the paper, for different types of behavior. We use that equation and it works. Now, when we look at the B and how B would be varying with particle size and fine content back in 2005 or 7 or 6, one particular paper helped a lot. That's McGree in 1961 from Journal of American Ceramics Society. They have big particle then mixed with smaller particle. As you see, as you increase the fine particles, then the bigger particle disappear in it. That developed the understanding and the mathematical formulation. But now with my student, we do 3D DEM simulation. Over here, we get 0% fine, that's been clean sand, about 10,500 particles. This one, 5% fine, about 66,000 particles. And then we have 10% fine, about 130,000 particles. So as you see, we increase a number of percentage of fine content. The problem become very, very difficult to run within a reasonable time in computer simulation. But when you do the test, we see at critical state, this clean sand develop a soil skeleton structure, force structure like that, a high density structure. And with that, you can assume this soil would take higher strength. When you have 5%, despite of 66,000 particles, the skeleton structure is far less dense. From that, we expect that there would be lower strength, and 10% is even lesser. So it tells us when we increase fine content, when a natural soil has fine content, it has natural tendency of getting lower strength. So liquefaction problem is worst for sand with fines. We have another parameter over here we call a strong contact between fines and the ratio between a strong contact between fines and coarse particle. But this one is 0.01, that's been 1%, and this one for 3%. So as you see, as we increase fine content, that indicate the active fraction of fine is increasing. So it's consistent with the theory we used. Now over here, we can see clean sand has a higher critical state line, sand with 10%, 5% fine is over there, and 10% fine would be over there. And this is QP path, this is M line, the critical state at the end of the test. So it tells us even for same void ratio of the soil, sand with fine would have lower strength. Let's see a few applications. First, I will look at the critical state side. So these are the sand test data, Sydney sand with the modular fines. This is the critical state line for clean sand. By the way, this is y-axis as a void ratio, and x-axis is the mean effective stress in a critical state. This is 5%, 15%, 20%, and 30%. As we increase fine content, as we expect the critical state line going down. Each of these fine and critical state framework is good enough to do further analysis, but in this case, as you see, it's not possible because you have to do test for all these different fine content and develop the framework and do the analysis. And then if you realize if you have a soil of 10% fine, you do not have the data. So what we have there done over here, this y-axis void ratio, we transport to equivalent granular void ratio. So everything merged with the clean sand data. So clean sand critical state line, basically the critical state line in equivalent space for sand with fines. When you have the critical state line, we can use the Bain and Jeffries concept to define a state parameter. A state parameter is nothing but void ratio of a soil and the void ratio on the critical state line at same P. That's mean a state parameter combine the effect of density E and P. Now, if a soil is above the critical state line, that means state parameter is positive, it would be contractive and liquefiable. If a soil state is below the critical state line, it would be dilative and non-liquefiable. But when we have fine content, then we have many lines and we merge the equivalent critical state line. From that concept, we can have equivalent state parameter in the same way. That will combine the effect of EP and fine content. Now let's see one example use of this theory. We use Ahmedabad sand to assess liquefaction. This is clean sand data. This is quarry dust and different percentages of fine content grain size distribution. These data come from Das and his other works with Professor Sitaram. But when I use this data in equivalent space, this is the critical state line we gave for sand with different fine content. Now, for critical state analysis, we need to estimate what would be the cyclic stress ratio we would expect from an earthquake that we can do from this analysis, simplified method from seed and idris. But in experimental setting, we do a triaxial cyclic loading test where sigma d is the magnitude of deviatory stress and sigma prime is the confining stress. As we have higher cyclic stress ratio, this magnitude would be higher and number of cycles to liquefy would be lower. So what happened in this graph, y-axis is cyclic stress ratio and number of cycles. So number of cycles required to liquefaction would be lower for higher cyclic stress ratio. And for lower cyclic stress ratio, number of cycles would be higher. So we get a line. But if we change the void ratio, if we change the confining stress, it would be different lines, but same trend. In this figure, we have additional complexity. We have fines content. For each fine content, same global void ratio, different lines. So this is a problem. So what we do over here, we try to estimate what would be the cyclic resistance ratio for an equivalent 20 cycles of loading. So that depends on the magnitude of earthquake and fault characteristics. So 20 number of cycle and respective cyclic resistance ratio is cyclic resistance ratio at 20 cycles. If we get all the data and plot them in this figure, so this is cyclic resistance ratio and this is equivalent state parameter, they come to a nice trend irrespective of different fine content. Now we collected a data from Raju who worked with Professor Sitaram. There was a SPD test in passport office near to the Sabramati River. This is the grain size soil type you can see with different fines content. And they have SPD data is varying like this. In conventional liquefaction analysis, we have, this is cyclic stress ratio of resistance ratio and corrected SPD count. For different number of cycles, we have different boundary curve. For example, if we have a SPD value, correct SPD value 15, if it is here, then it's liquefiable for higher fine content, but for not liquefiable for higher fine content, but liquefiable for 5% fine content. We can use the same concept to analyze that. So what we have done over here, this is the cyclic stress ratio and corrected flow count. These data we plot over here, SPD data, and this is the boundary curve come from yield. What do you see? It's to the right of the curve, so they are non-liquefiable. The site didn't liquefy during Bhuj earthquake, but the same analysis we could do equivalent state parameter, and this is the boundary line we get. Anything on the right side, these data point, it's mean non-liquefiable. So what is the advantage of that? This theory comes from theoretical background, whereas the empirical chart, it's a developed chart that changes with new data sets. To develop the constitutive model, we need at least 4 different strategies. One is elastic parameters, yield surface. If it is a model for critical state, then critical state parameter, dilatancy of flow rule, or hardening rule, or plastic modulus. So let's look at the elastic parameter. How do you handle that? This is Harding equation or Chomsky equation to estimate the elastic parameter G max. This is the equation. What do we did over here? We just replace E by E star for different fines content. And this is the measured data, and this is the predicted data using clean sand equation part replacing E by E star. It matched very well. One thing you would notice, clean Houston sand had higher G max than 30% Houston sand with 30% fine content over here. But despite of that, it predict well. There is other data set we analyze it and it did the same. For critical state parameter, because all the critical state line merge with the critical state line of clean sand, so the parameter doesn't change, it remains same. So we just use the parameter for clean sand critical state lines. When you look at the dilatancy parameter, it's the bounding surface model we are looking at. So it has a function of psi, all the parameter, this D, and there should be stress ratio over here is missing. All the parameter D naught and M would be same, only we change side to side star, as I explained before. The plastic modulus and hardening parameter would be the same thing over here. Everything, every parameter remains same. We just change to side star, G to G star, side to side star over here. And that's the model is ready. So what does it mean? We would have a model for a range of fine content with one set of parameters, that is for clean sand. So these are the key equation I put and the values for clean sand over here. Then look at the prediction. If we look at the prediction, this is Davidic stress ratio and mean effective stress path for different 15, 20, and 30% fine content. And these are the model prediction. I put two model over here. The model I explained is the first one, and the second, the blue line, was another model with fabric evolution. So at the beginning, I said, forget about the fabric, just focus on the word ratio. And we know that is not correct. So I avoid the complexity over there, but actually we can consider the fabric over here. In this figure, both of them is quite well. So why do you need fabric? So if you look at the dense soil behavior, 0 and 15%, these are the path. Without fabric, this is the dotted line prediction. You see, dotted line is much more contractive. It doesn't capture the behavior, but when we have fabric, it's much more close. So fabric is needed to some extent. If we want to know cyclic loading behavior, we again choose one of the Duffalius model for 2014. This is exactly same formulation. There is little tricks. They change the yield function slightly so that they can play with cyclic behavior, and they also have a constant fabric parameter. This fabric is different than the fabric evolution. We check the behavior. Just one data. I didn't present the real prediction, just hypothetical curve over here. This is clean sand. We can see this is the clean sand behavior. This is model prediction. And this is cyclic loading behavior different. We could have positive or negative or conventional cyclic loading. But what do we see over here? A little bit deviation with these real test and the monitoring test data. And when you look at the pore water pressure generation, the real soil develop a little bit slower, but the model predict quite fast. So these are the deviation we observe over here. Is the time up? Now, this is my conclusion or my understanding over here. This works very well with uniformly graded sand. It says a single type sand, a single or poorly graded sand with non-plastic fine. There is no doubt. If we substitute E by E star, then we can predict G max equivalent granular state ratio, steady state line. That should not be any problem. If we substitute E and E star and psi star in existing constitutive model, it seems it works. There would be some discrepancies. This could be improved. But what I have shown over here, we just choose the parameter from clean sand and use it. That works. But I do not see much work on this field. There is few research, like 6-7 research group working on this, but not much work report on plastic fines, not within this framework. There is some work, but not looking at equivalent granular concept and well-graded sand. The framework I presented today over here, we call it sand with fine section. It's not necessarily have to be fine sand. If we have sand and fine actions, then we could use it. So we need more research on this. Thank you. Any questions?
Professor Rahman, I would like to say, first time I had the concept of equivalent void ratio, how it affects, and you have very nicely explained step by step, where initially the fine particles are filling up the only voids, then later they are in between the two sand particles and how they affect, how to take care. And
thank you.
I mean, first time I'm hearing that sort of concept. Maybe more than that, you have very nicely explained the implications of that. And it's a very nice presentation. And,
thank you.
I would request Dr. Jayarajan to say, take it forward.
Anyway, thanks a lot, Professor Mizanur, Rahman, a wonderful presentation. And I think that it will be definitely a part of a very latest research. And I think that if we push much more ahead, we may find something new discovery, I think, because the concept, you know, we are transforming a very complicated phenomenon into a mathematical equation. It's unimaginable. It's a very good kind of, and I'm very sure that this will have a very, what I would say, practical significance or implication, at least in the process of evaluation of the liquefaction, where the percentage finds will have a very markedly influence on the science. So all the best for your research. Thanks a lot for sharing your wonderful, findings with such a very nice audience. Thanks a lot.
Professor
Thank you
Rahman,
very much. Yes.
very good lecture, very informative. And I also worked on critical state behavior of granular media using DM simulations, which of course Vinod took over. Then I have one thing.
Yes.
How did you take this fabric into account? Briefly, you can, because this is not today's scope.
Yeah. No, it's a part of that. For this particular model, it has a two things. We can look at fabric in from DM simulation because you have the fabric tensor. From that, we can play with different. But for this particular model, it's actually need a fabric evaluation rule. So it start with the initial fabric, and how the fabric will change. That depends on for this model is plastic strain. So it's actually well known as ACST, anisotropic critical state theory.
Correct.
So it's the recent work with Professor Lee and Defalius, and then we took over for sandwich finds. So what does it? This rule is saying the three condition of critical state: constant Poisson ratio, constant Q, and constant P is not enough to define a critical state. That should be a critical state fabric. So fabric evolved from initial fabric to critical state fabric. And that critical state fabric can be present in terms of normalized value of 1. So we have some publication on these as well. We try to evaluate that through the DM simulation, how that evolved during sharing. And then we compare with this constitutive model, because constitutive models formulation comes from plastic theory of metals, not from DM simulation. So we're now trying to compare them and reduce the gap in solve.
Regarding this fabric, we use some anisotropic coefficients, PhD
Yes.
kind of a thing. We were using that for the force signs, for normal force, tangential force, and also for fabric. We were characterizing through anisotropic coefficients. As the shearing develops, the coefficients would grow. So that is what I was interested to know, how actually that has been taken here. Thank you.
Thank you. From constitutive model point of view, it's a different way of formulation than what we do in DM.
Yeah. Good, sir. Excellent presentation.
Okay. Thank you, everyone, for
Thank
giving
you,
me the
Mr.
opportunity.
Rahman. And